All right, so welcome to Commutative Algebra Seminar. Good morning to some and good afternoon to some others. And these are different times, but we are happy to be together, even in online mode. Today we have with us Professor Ken-ichi Yoshida from Nihon University. He will talk on lower bound on Hilbert-Kunz multiplicities and some related results. We are very happy to have him in this seminar. Participants can use chat box to ask their questions, and I will relay them during the seminar. And at the end of the seminar, we can have live interaction with Ken-ichi. So I now invite Ken-ichi to begin his seminar.
Okay. Thank you very much for my introduction. First of all, I'd like to appreciate the organizers, especially Professor Bama, for inviting me. And also, I must apologize to all of you for the delay of my talk because of my health. Okay, now let's start my talk. The title is here. This is the contents of my talk. So throughout this talk, let A be a Noetherian local link of characteristic P and clue dimension D, and let I be a primary ideal. And also assume that A is a finite. A finite means a properties map is a finite map. And also this condition implies that A is excellent by Kunz, and A is a homomorphic image of Gorentian local link. And so in this case, A admits a canonical module. Okay. Let me recall the definition of Hilbert-Kunz multiplicity. This notion has been essentially introduced by Kunz, and it was formulated by Monsky. As in definition 1.1, Hilbert-Kunz multiplicity can be defined as for any finitely generated A module, but we pay attention to the A itself in this talk. And so we call the Hilbert-Kunz multiplicity of I in this case. Okay. The Hilbert-Kunz multiplicity gives a refinement of the usual multiplicity. In fact, let K be a minimal reduction of I. Then this means Q is a parameter ideal, which is contained in I, which has the same integral closure of I. In this case, the multiplicity of Q is equal to the multiplicity of I. But the similar relation does not hold for Hilbert-Kunz multiplicity. For instance, please look at this example. In this case, Hilbert-Kunz multiplicity of M is equal to 2 minus 1 over N, but the Hilbert-Kunz multiplicity of Q is equal to 2. 2 means 2 is the usual multiplicity of this ring. Let me recall some fundamental lemma. If there exists a finite morphism, we can calculate the Hilbert-Kunz multiplicity of I using this formula. And also, if there exists a flat local homomorphism with a maximal ideal of B, N is equal to this M times B. In this case, the Hilbert-Kunz multiplicity of I is equal to this one. So Hilbert-Kunz multiplicity is preserved under extension in this sense. And in particular, the Hilbert-Kunz multiplicity is preserved under the completion in this sense. Okay. Probably associated formula for the usual multiplicity is well known for But Hilbert-Kunz multiplicity, a similar formula false. This is called associated formula for Hilbert-Kunz multiplicity. Using this formula, we frequently reduce a problem to the integral domain case. The proof of this formula follows from the additivity of Hilbert-Kunz multiplicity and the existence of Noetherian filtration. Let me recall the definition of tight closure. This notion was introduced by Hokusan and Huneke in order to prove some homological conjectures in that days. The relationship between Hilbert-Kunz multiplicity and the tight closure is like the relationship between the usual multiplicity and the usual integral closures. For example, this relationship is very important in some sense. The following Kunz theorem is a basic result in this area. For instance, this theorem implies a Hilbert-Kunz multiplicity of a regular local ring is 1, and also this theorem implies that any regular local ring is F-regular in the sense of the section 2. In general, Hilbert-Kunz multiplicity of any local ring of A is greater than or equal to 1. Okay. It's natural to ask this. This question: when does this formula, this equality hold? About 20 years ago, Watanabe and I proved the following theorem, which is a characterization of regular local ring in regular local rings in positive characteristic. This is also analogy of Nagata's theorem. In this talk, we give a little bit shorter proof instead of original proof in the papers, appeared in the papers, in our papers. Okay. Now let's prove. Now let's give a sketch of the proof of the theorem 1.10. We use the induction on clue dimension B, and also we may assume that A is complete. In particular, A is a homomorphic image of a Cohen-Macaulay local ring by a Cohen structure theorem. And also by associative formula, we may assume that Ash A is consists from only one prime P, and also A sub P is a field. Since A is a mix, associated problem of A is equal to the minimal of A is equal to P, the set of P, and so this condition implies that the S1 condition, cell condition S1, and also this condition implies that R sub 0. So we have A is reduced. And also 0 is equal to the radical of 0 means is equal P, and so A is a domain. Okay, so A is a domain in this case. Moreover, since it is universally catenary, so we have the following equality. Here we use the Kunz result. This lemma implies that the Hilbert-Kunz multiplicity of the local ring S sub P is equal to 1. Hilbert-Kunz multiplicity of the local ring S sub P is equal to 1. Therefore, induction hypothesis implies that A sub P is regular. And in particular, so A sub P is Cohen-Macaulay for every prime P in punctual spectrum. And so under some mild assumptions, so A is FFC. Okay. And so in what follows, assume that A is FLC, finite local cohomology. This means A admits a standard SOP. Namely, such a standard SOP, A sub 1, A sub 2, A sub D, is satisfied the first displayed formula. Okay. Let Q be a parameter ideal which is generated by this standard SOP. In this case, clone capture property for tight closure implies the foreign inclusion. Sigma ideal, this ideal is this ideal. And also Q star is a tight closure of Q. And so we get E sub multiplicity of Q minus colength of A over Q star is greater than or equal to multiplicity of Q minus colength of A over sigma is equal to this one. And this is non-negative. So we have the following inequality. Okay, so in the next step, we prove the opposite inequality. In order to do this, the key lemma is the following filtration lemma. This means difference between the Hilbert-Kunz, sorry, look at second statement. Second statement. This means the difference between the Hilbert-Kunz multiplicity of two ideas of colength 1 is at most Hilbert-Kunz multiplicity of A. This is this means a filtration lemma. So our assumption implies that Hilbert-Kunz multiplicity is equal to 1. So that by the first, sorry, third statement of the this lemma implies that Hilbert-Kunz multiplicity of I is less than or equal to, sorry, this is, sorry, this is a mistake. So colength, okay. This is colength of A over Q star. So we have the equality, and also this local cohomology vanishes. These local cohomology vanish for I is equal to 1, d minus 1, and also zeroth local cohomology is always 0 by the assumption. So A is Koema-Kore. Okay, this is A is Koema-Kore. This implies A is Koema-Kore. So in what follows, assume that A is Koema-Kore. Let I be an imprimary ideal and take a parameter ideal Q, which is contained in I. By also filtration lemma, we get the following two inequalities. The first inequality shows Hilbert-Kunz multiplicity of I is less than or equal to the colength of A over I. And also the second inequality implies that the opposite inequality, because this Hilbert-Kunz multiplicity of Q is equal to the multiplicity of Q, and also this is equal to the colength of A over Q, because A is Koema-Kore. So this is gives the opposite inequality. So we get the equality, and so we can apply I is equal to the M to the bracket Q. Bracket Q is so we get the following colength is equal to the Q to the D. So Kunz theorem implies that A is regular. This is a proof of the theorem 1.10. This proof is a little bit shorter rather than the original one. And also, This as a result, we pose the answer to the above question. This means Hilbert-Kunz multiplicity is equal to 1 if and only if the multiplicity is equal to 1. The proof is essentially follows from the previous theorem. In this case, using associated formula, we can associate A is equal to we can show that the associate A is equal to the only one prime P, and so A over P is a complete local domain, so are mixed. So we can apply the theorem. So A over P is regular, and this implies that the multiplicity is equal to 1. And also we can apply the associated formula for usual multiplicity. So we get the multiplicity is 1. And this is a proof of corollary. This gives a answer to the above question, first question. And so these are examples of Hilbert-Kunz multiplicity of 1. For example,
Ken-ichi, I have a question. On the previous slide, don't need unmixedness hypothesis.
Sorry.
EHK equal to 1. EHK equal to 1 if and only if EA is 1. There no unmixedness hypothesis is required there.
In the corollary?
1.13, yeah. Ring is not unmixed. It's any local ring.
In this case?
Yeah.
1.30? We don't need to assume that it is unmixed.
Oh, it comes out in the proof. Okay.
Okay.
Fine. Fine. Thank you.
Okay. Okay. Now, let's. In the example 1.14, in this case, in this first example, A is not equidimensional. And the second one is a case unmixed, but not unmixed. And the third one says A is a local domain, but not unmixed. Okay. These examples give Hilbert-Kunz multiplicity 1. Okay. Section 2. Let me recall the definition of F regular or F rational local rings. Weakly F regularity is F regularity defined by the tightly closeness of all ideas. And also strongly F regularity is F regularity defined by splitting of progress maps. Details is here. And in this talk, we don't distinguish two notions for simplicity. Okay. We call it F regular, strongly F regular, or is weakly F regular. Also, we call it F regular. And F rationality is defined by tightly closeness of parameter ideas. Every parameter ideas over some parameter ideas. And also, we need to assume that it's co-equivalent. Roughly speaking, Q-Gorenstein F regularity correspond to log terminal singularity, and the F rationalities correspond to the rational singularity. Also, Kunz theorem says any regular local link is F regular, strongly F regular. Throughout this section, we always assume that A's are mixed. Okay. In this case, our theorem claims Hilbert-Kunz multiplicity of 1 implies that A is F regular. This means A is regular. So regular means F implies F regular. So it's natural to ask the following question: Hilbert-Kunz multiplicity, if Hilbert-Kunz multiplicity is small, then does A have a good ring theoretic property? Wow. We consider local rings of small multiplicity. For instance, let A be a hypersurface of multiplicity 2 or degree 2. This condition is equivalent to the A is a Cohen-Macaulay local ring of multiplicity 2. In this case, the situation is very clear. If A is F regular, then the Hilbert-Kunz multiplicity is less than 2. If A is not F regular, then the Hilbert-Kunz multiplicity is equal to 2. Look at these examples. In this, the last example, it's not F regular. In some sense, as a working hypothesis, we pose the following conjecture. Assume that there is a mix of Hilbert-Kunz multiplicity is less than 2. Then the A is F regular. Note that this assumption does not imply that the multiplicity 2 is equal to 2. Look at these examples. In the second or third examples, multiplicity is 3 over 4, and Hilbert-Kunz multiplicity is less than 2. In this example, clue dimension 3, and in this example, clue dimension 4. And also, these rings are not Gorenstein. So this condition does not imply the Gorenstein in general. In what follows, we introduce Brickle-Enescu theorem and Abel-Baha-Enescu theorem. In this theorem, multiplicity is the general multiplicity, E. The following Goto-Nakamura's theorem plays a key role in the proof of Brickle-Enescu theorem. Also, in order to prove first theorem means Hilbert-Kunz multiplicity is 1, implies that it is regular. We use the Fresnel-Peltier theorem in the original proof, but we don't use it in today's proof. And Goto and Nakamura proved this theorem by using this idea and formulated the following complete form. Maybe Professor Kui proved a more general form, but I couldn't find his paper. Okay, this is a Goto-Nakamura theorem. This theorem says Hilbert-Kunz multiplicity of Q is greater than or equal to the co-length of A over Q star. And also equality false truth, so A is Cohen-Macaulay and a fraction. Okay. Let me introduce a Brickle-Enescu theorem. Under this mild assumption, Brickle-Enescu theorem says this Hilbert-Kunz multiplicity is less than E over E minus 1, then the A is Cohen-Macaulay fraction. The proof of sketch is here, and but we don't. We skip the proof here. This idea is main point is Goto-Nakamura theorem and filtration lemma in the first proof, first statement. Okay. In order to prove Abel-Baha-Enescu in order to state and prove Haber-Inequality theorem, we need matrix duality in some sense. In fact, we prove the following lemma. In the proof, one can use Hilbert-Kunz multiplicity of a canonical module. As the corollary of the lemma, the following statement follows. If A is not Gorenstein, this means type is greater than or equal to 2. So we get the following inequality. So we compare this assumption. So we get the following result. Haber-Inequality theorem. In fact, this theorem follows the first statement of this theorem follows from the above observation. In fact, this assumption implies that there is Gorenstein. And in the Gorenstein case, if rationality and if regularity is equivalent. So we get the following theorem. We record our conjecture in some sense working hypothesis. Assume that there is a mix and Hilbert-Kunz multiplicity is 2 is less than 2, then the A is F regular. But does not imply this condition does not imply that there is Gorenstein. Okay. Next section, section 3. In this section, we consider the following inequalities with respect to multiplicity and Hilbert-Kunz multiplicities. The left-hand side follows from the fact that Fulvey's Q's powers is contained in the ordinary Q's powers. And on the other hand, the right-hand side follows from the Lehi's formula. In two-dimensional cases, we get the following theorem. For example, this gives a lower bound on Hilbert-Kunz multiplicities for singular means non-regular, a mixed local length of dimension 2. In fact, Hilbert-Kunz multiplicities, in this case, Hilbert-Kunz multiplicity is at least 3 seconds. In a joint work with Jeffries, Nakajima, and Watanabe, we proved the following theorem. This is a higher analog of the previous theorem. We assume that the Coulomb dimension is greater than or equal to 3. But this is not the best lower bound, even if dimension 3. This is strict inequality. In the proof of this theorem, key idea is the following lemma, but we don't explain details here. Because we have so enough time to explain. So we pay attention to the 3-dimensional mixed singular local links. In this case, we have the following theorem, this theorem, which gives an analog of the theorem in dimension 2. Indeed, for this hypersurface, we attain equality. In fact, for this ring A, Hilbert-Kunz multiplicity is equal to this one, and also multiplicity is 2, so we get the equality. And in fact, under some mild condition, we can characterize the equalities. Okay. From this theorem, we get one corollary. By virtue of this corollary, we get some structure of a mixed local link of Hilbert-Kunz multiplicity is less than 2 in dimension 3. We obtain that A has minimal multiplicity. Minimal multiplicity means the maximal ideal of M is equal to the multiplicity plus cool dimension minus 1. In this case, cool dimension 3. So in this case, this condition means this equality. And also next example, this example is only one a mixed local link of Hilbert-Kunz multiplicity is less than 2, and which is not Gorenstein among non-Gorenstein local links. And this means this condition and means in this case Gorenstein means not non-Gorenstein means multiplicity is greater than or equal to 3. So So in some sense, this is a problem. Find all Kolyma-Colle local domains of dimension cool dimension 3. Multiplicity is equal to greater than or equal to 3, and Hilbert-Kunz multiplicity is less than 2. In section 4, we discuss the lower bound of Hilbert-Kunz multiplicity of singular and mixed local rings. We have proved that in the first theorem, A is a singular and mixed local ring. Then the Hilbert-Kunz multiplicity is greater than 1. So it's natural to ask the following question: what's the infimum for fixed P and fixed P and fixed multiplicity E? Cool dimension is less than or equal to 1. Problem is very easy. So we need to assume that the cool dimension is greater than or equal to 2. In order to state our conjecture, we prepare some symbols of local links A sub PD as follows. A sub PD is so-called A1 singularity. Characteristic P is odd prime. The equation takes a more familiar form, this one. Let me give some history of Hilbert-Kunz calculation of Hilbert-Kunz multiplicity of A sub PD. Han and Monsky gave an algorithm to compute this Hilbert-Kunz multiplicity for a large P. And also Gessler and Monsky proves the existence of limit of Hilbert-Kunz multiplicity. And this limit is equal to this one. A very curious one, I think. By some observations, we pose the following conjecture. Hilbert-Kunz multiplicity of A sub PD is a decreasing function on P for fixed D. And this implies that the second statement. This statement is the original conjecture. Original statement in the original conjecture. But the first one is a little bit new conjecture. In general, we pose a following conjecture for odd prime P, or odd conjecture. Let A be a mixed singular local link, and P is auto prime, then the Hilbert-Kunz multiplicity of A is greater than or equal to the Hilbert-Kunz multiplicity of A sub PD. And the equality false, then the completion of A is isomorphic to A sub PD. This is the original conjecture for auto prime P. Let me introduce the affirmative answers. Roughly speaking, cool dimension is equal to 3 or 4. Cool dimension is B is less than or equal to 4. In this case, the conjecture holds true. And also, if D is a 5 or 6, then the conjecture for inequality is false. But we don't know equality false, as I know. And also, my colleague Shimamoto and Enesk proves the same inequalities for complete intersection local links. These are affirmative answers, I think. Let me give some new conjecture, something new conjecture for characteristic 2. In this case, expected form of Hilbert-Kunz multiplicity is very simple, I think. This one and this one. This formula, this conjecture is very concrete, but I can't prove it yet. For cool dimension is equal to even, the above conjecture is true. We can prove this one. But cool dimension is odd case, it remains still open, I think. In general, Hilbert-Kunz multiplicity of A sub PD is depends on P in general. Look at this example in the whole dimensional cases. So in the final of this section, we pose the following improved conjecture. Okay, this is improved conjecture. So let A be a mixed singular local link. In this case, if D is odd, then the completion of A is isomorphic to A sub PD, or Hilbert-Kunz multiplicity is greater than this number, this guy. And also, this is improved conjecture. Okay, so in the final of this talk, we discuss F signatures. In what follows, we assume that A is a local domain, a finite local domain, and Frobenius push forward is a finitely generated A module. So this means that Frobenius push forward is a finitely generated A module. In this case, Hilbert-Kunz multiplicity of A is equal to this one, this limit. We can regard it Hilbert-Kunz multiplicity as a limit. And in this case, F signature of A is defined as follows. In some sense, this is a F rank. This N is a F rank of this Frobenius push forward. And this is a ratio of F rank and rank. Okay. And also F signature always exists by Tucker's result. The following Abel-Baha logical theorem means F signature is an important invariant for F regular rings, because if A is not F regular, then the F signature is equal to 0. Now let's consider the simple example. Let A be a quotient singularity of such a quotient singularity. In this case, F signature is equal to the 1 over the order of the group G, and so is at most 1/2. But in general, similar question has no answer even in dimension 3. So we pose the following question. Let A be F regular singular local domain of clue dimension D is greater than or equal to 3. Then what's the upper bound on F signature? Upper bound on F signature. We discuss this problem question. Assume that is Gorenstein. In this case, we can compute F signature using this simple formula. In fact, if Q is a parameter ideal and put I is equal to Q colon M, so F signature is equal to the difference of Hilbert-Kunz multiplicities. For example, in particular, A is a hypersurface of degree 2 or multiplicity 2, then the F signature is equal to 2 minus Hilbert-Kunz multiplicity. So following conjecture is natural in some sense. Let A be a singular, a mixed local, F regular, a local ring of clue dimension D is positive. Then the F signature is less than or equal to this number, 2 minus Hilbert-Kunz multiplicity of the A sub PD. And equality falls if and only if the completion of A is isomorphic to A sub PD. Okay. Okay, so let A be a finite Koyama-Kuru local domain, a Koyama-Kuru local domain, but not A is not Gorenstein. Then the Hilbert-Kunz multiplicity is less than or equal to this number. And in particular, F signature is less than or equal to 1/2. So this proportion says if A is a Koyama-Kuru F regular, but non-Gorenstein local rings, the upper bound of F signature is 1/2. We give a proof, but we skip a proof here. So okay. This let me recall the definition of Ulrich module. Ulrich module in the classical sense means maximal Koyama-Kuru A module, which satisfies this equality force. Minimum number of generators is equal to the multiplicity of M. In general, for any MC maximal Koyama-Kuru modules, we have the inequalities. The minimum number of generators of M is less than or equal to the multiplicity of M. So this theorem claims For non-Gorenstein F-regular local links, this equality force, if and only if probability push force is some determined structure of such a finite direct sum of A and canonical module and Ulrich A modules. For every E is positive. So this module structure of the Frobenius push forward is determined clearly in this case. This is a definition of finite representation type, so-called FFRT. Of course, if finite representation type is a typical example of FFRT, and also non-trivial examples are toric links. This is FFRT. Using this notion, we can characterize Koyama-Correa non-Gorenstein local links with F signature is equal to 1/2. We can characterize such a condition. The second statement says A is FFRT with FFRT system is A and canonical module, A itself and canonical module. In this case, Hilbert-Kunz multiplicity is equal to the this number. The typical example of this such a link is here. Second Veronese subring of a homoparity ring. For auto prime D, this ring is not Gorenstein, and even prime, even integer D, this ring is Gorenstein. But in both cases, F signature is equal to 1/2. We can in this in a paper, so we can characterize such a link in some extra assumption under some extra assumptions. And in the Gorenstein case, we can prove a similar result. In this case, this gives an upper bound on Hilbert-Kunz multiplicity in terms of the signature and multiplicity. In the last part, we discuss upper bound on F signature in dimension 3. Okay, our conjecture claims F signature is less than or equal to 2/3. In fact, this number is 2/3 is equal to 2 minus 4/3. 4/3 is lower bound of Hilbert-Kunz multiplicity in dimension 3. But we cannot prove it. We cannot prove this conjecture, but we give a partial answer here. Let A be a three-dimensional F regular local domain, which is not regular. Then the F signature is less than 5/6. In this proof, we may assume that A is Gorenstein. If not, F signature is less than or equal to 1/2. So by this proportion, the previous proportion, we have following inequalities. And on the other hand, theorem, the 3.5 implies that this inequalities. Okay. And so we combine these inequalities we have the following inequalities. And so this number, F signature minus 1, is negative because A is not regular. So SA is not equal to 1. And also F signature is always less than or equal to 1. So we have the following inequality. And so multiplicity is of course positive. So F signature, this number is negative. And so we get following inequality. This cool dimension 3 in dimension 3, we have another inequalities, but we cannot prepare such a statement, so we skip here. Thank you very much for your attention. This is a special day. Happy birthday, Ramanujan. Thank you very much.
Okay. Thank you, Ken-ichi, for your very interesting talk and so many conjectures. And so we now open for discussion. Yeah, any questions?
So yeah, I have a question. I'm Vijaya Lakshmi here. So you for quadratic hypersurfaces,
Sorry.
and the quadratic hypersurfaces in characteristic 2, you have computed the HK multiplicity when dimension is even. So when dimension of a quadratic hypersurface is even
number.
Even number. It's not an odd dimension, it's an even dimension. So my question is, how did you compute the HK multiplicity?
Sorry, I cannot hear your voice.
I don't know. If can I repeat the question, Vijayalakshmi?
Yeah.
So you have done some calculation about quadratic hypersurface, Hilbert-Kunz multiplicity of quadratic hypersurface. So her question is, how are you computing that?
How are you compute? We use some matrix. So, but in general, it is difficult to compute.
No, but you have computed for even dimensional case, but you said odd dimensional case, it's open.
Yeah, maybe open.
It's an open question.
Open question.
So there you couldn't use a Hans-Monsky algorithm?
Hans-Monsky proves that algorithm, but they didn't give us cross formulas.
Okay. Okay, yeah, that's it, yeah.
So is it open even in dimension 3 for the, in that case, dimension 3? It's open.
You know, any Briscoe type, sorry?
Say the odd dimensional case is open.
In general case is open.
But in dimension
3?
I think dimension 3 is okay.
Dimension 3 is fine.
Okay. I think so.
Yeah.
So
any other questions? There is a question in chat box. Yeah, from Ehsan Tawanfar. Ehsan, are you there? You can ask your question.
Sorry.
There's a question from Ehsan. There's
Do
a
you hear
theorem.
me?
Yeah.
I can hear.
If you hear me, there is a theorem by Professor Hunike that a ring which is Sn and has multiplicity less than n is Cohen-Macaulay. This is about ordinary multiplicity. My question is that whether there is whether this hold for Hilbert-Kunz multiplicity in place of the ordinary multiplicity, or is there a variant or any hope to prove such theorem?
Sorry, the last part. I can hear the last part.
My question is that whether there is any hope to prove a variant of the theorem I mentioned for Hilbert-Kunz multiplicity in place of the ordinary multiplicity.
Sorry, I don't know.
Ken-ichi, the question is related to Hunike's theorem, which generalized the Nagata's theorem. Nagata's theorem was for unmixed local rings of multiplicity 1, and Hunike generalized this for multiplicity less equal to n, and Sn condition implies that the ring is Cohen-Macaulay. So his question is, do we have so yours and Watanabe's theorem says that if the ring is unmixed and multiplicity is 1, then the ring is regular. So it is natural to ask and
I see.
Hunike's theorem for Hilbert-Kunz multiplicity.
I see, but I don't know. I have no answer.
Right.
Thank you. Thank you so much.
Thank you very much.
Okay, that's a good question, Ehsan. Yeah.
Thank you.
Yes, a good question, I think.
Now, many of the bounds, they just involve the multiplicity and Hilbert-Kunz multiplicity. They are relating, and if the extreme case occurs, then the ring is nice. Now, there are other Hilbert coefficients of the given maximal ideal of the local ring, like E1, E2, etc. And in some situation, we do have a coefficient of q to the d minus 1 also. It does make sense, right? So are there such inequalities known for other coefficients of Hilbert-Samuel polynomial and the coefficient of q to the d minus 1? Because all the inequalities that I see in your paper, they only involve multiplicity and Hilbert-Kunz multiplicity, which are leading coefficients. So one would expect that there may be such relations between other coefficients of Hilbert-Samuel polynomial and let's say the coefficient of q to the d minus 1. I mean, Vijayalakshmi in her paper, one of the papers in graded case, she does give interpretation of the coefficient of q to the d minus 1. So are there such inequalities known between, say, the Chern number of a parameter ideal and the coefficient of q to the d minus 1, whenever it makes sense?
I think the second coefficient was given by Huneke-Monsky.
Okay.
Not by
One is okay.
that for the normal excellent ring, and the interpretation, some interpretation was given by Kurano. What we did actually exactly related the second coefficient of the Hilbert-Kunz function with the second coefficient of Hilbert-Samuel function for projective toric varieties.
You mean E1 or E2? What do you mean by second?
E0 and E1.
E1. Okay. So the next
E0
one.
and E1 relates to Hilbert-Kunz multiplicity and the second coefficient of Hilbert-Kunz function.
Okay.
For projective toric varieties, it's a very specialized.
I mean the coefficient of q to the d minus 2 you are talking about?
Yes, yes.
Okay. Okay.
I see. I remember.
I mean, it's a very mysterious number that is very clear. Yeah. And in one formula you mentioned you looked at the ring of invariants of power series ring in two variables, and there was exact formula for the Hilbert-Kunz multiplicity. Do we know the Hilbert-Kunz function in that case?
I don't know.
The ring of invariants of a finite group acting on power series ring in two variables. I think you mentioned that the F signature is 1 over order of G. And so do we know the Hilbert-Kunz function of that ring of invariants? The multiplicity is, I think, 2 minus or 1 minus 1 over order of G, right? But multiplicity is also known. But do we know
No.
Do we know the Hilbert-Kunz function?
No. We can calculate.
Okay. Okay. Yeah, that may reveal some relation between the Chern number and I mean, this is dimension 2 case and the other Hilbert coefficients and Hilbert-Kunz multiplicities and coefficient of q to the d minus 1. And, yeah. So we can calculate both the functions in that case. Yeah. Okay, any other questions? Yeah, it is fun. Okay, I don't see any further questions. Yeah. So, Ken-ichi, it was very interesting to listen to you. And thanks for coming online, although it is late for you in Japan. But we all enjoyed your talk, and thank you very much. And we can close the meeting. Yeah.
Thank you very much.
Yeah.